Alright, 5-3 in Advanced Algebra 2. Since you missed class, what we did in class is we did a little dice rolling experiment where people rolled two different six-sided dice about 50 times just recorded the results. It's just kind of an idea to see all the different possibilities that could happen when rolling a die. So I'm not going to make you do that by way of the video, but here's one die. So like you got a die up here, and on that die, remember you could roll a 1, a 2, a 3, a 4, a 5, or a 6 because it's a six-sided die and it's fair. Same thing here. Here's the second die, 1, 2, 3, 4, 5, 6. So like what we're filling out this chart for is like, let's say when you rolled the two dice, you saw a 1 and a 1. Isn't that a total of a 2? Like we're trying to find the sum of those two dice. And if you rolled a 1 on this die, let's just call this the red die, just to make things nice and neat. Call this like the green die. Like if you rolled a 1 on the red die and a 2 on this, wouldn't you get a 3 out of that situation? And a 1 on the red die and a 3 on this, you'd get a 4, and etc. So what I'd like you to do is pause the video and fill out this chart completely. And as you can see here, this is all of the possible sums. Like the biggest number you could ever get is a 12, right? Because 6 and a 6, you roll together, it's 12. So now let's answer these questions. What sum appears the most? Well, I hope you kind of also notice this cool little diagonal pattern that's going on. And doesn't the 7 show up the most in that situation? Like there's 1, 2, 3, 4, 5, 6 different ways to roll a 7. And a lot of people, since we didn't since you didn't actually roll them, it's like, hey, how could that be? It's like, how can you get a 6 and a 1 and a 6 and a 1 be different things? Well, here it's you rolled a 6 on the green die and a 1 on the red die, and up here this is a total different situation. Now you had a 6 on the red die and a 1 on the green die. It's like that's two totally different things right there. So that's supposed to be green, by the way. So it is possible. So what appeared the most? The 7. Which sum appears the least? Well, the 2 and the 12 appear the least, right? They both appear at one time. Find the probability of a 5. Well, there are 36 total different possible outcomes, right? We have them all listed right here. Probability of the 5, there's 1, 2, 3, 4 different ways to do that. So 4 out of 36, which we can reduce that. 4 goes into each one of those, so that would be 1 out of 9 in that situation. Find the probability of 9. Well, that's 1, 2, 3, 4 different ways to do that. So the cool thing that we just figured out right here is it is equally likely to roll a 9 as it is a 5. You've got the same chance of doing that. Find the probability of rolling a 13. Don't think that's going to happen, man. We can't roll a 13. So that would be 0. That is impossible. Find the probability of rolling a sum of at least 6. So at least 6, we've got 1, 2, 3, 4, 5 ways here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 26 ways out of the possible 36. So we could reduce that if you wanted to, just like we did in class the other day. 26 divided by 36, math, enter, enter. And it's like a 13 out of 18 chance of that, which we'll just leave them all as fractions today. 13 out of 18 chance of that happening. Well, I'll tell you what, we might as well do the decimal. So it's about 72.2%. So that's probably pretty likely to roll at least a 6 in that situation. So very, very likely. Now we can go to a casino game, craps. You may have heard of it, you may have not. They roll two fair six-sided dice, and then the person that rolls the dice is called a shooter. They roll the dice, and other gamblers just kind of bet on what the sum of those two dice are. Well, like one of those bet is called the field, as you can see here, like the craps tables, that green felt and all that stuff. If you place your bet on the field, the gambler's a winner if it's a sum of 2, 3, 4, cross out that 5 because that's a typo. So you win if a 2 shows up, a 3 shows up, a 4, a 9, a 10, an 11, or a 12 is rolled. And quite honestly, like if you roll a 2 or a 12, they pay more than those. This particular says that 2's pay double and this pays triple, meaning if you bet $1, they'd give you $3. But who cares about the payout? Let's just do the magic mathematical, I didn't want to say magic, let's do the math probabilities. Do you feel that it is a wise bet to bet on the field? So again, that's if you roll a 2, a 3, a 4, a 9, a 10, 11, or a 12. Well, to the untrained mathematician, this looks like a great bet because they're like, oh, look, 1, 2, 3, 4, 5, 6, 7 different things would make me a winner. Well, that's not true. There are 36 total possibilities, so let's count up all the winners. You'd win if you rolled a 2 or a 3, so I'm just going to count up. There's 1, 2, 3. There's 3 things that would make you a winner. You can win a 4, so 4, 5, 6. 6 ways to win right there. Now 5 is not a winner, 6 is not a winner, 7 is not a winner, and 8 is not a winner. So you start winning on the 9. So we had 6 already, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 ways to win. 16 ways to win. Well, let's look at all the ways to lose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 ways to lose. Is the field the wisest bet in the world? No, it's not. No. There's more ways to lose than there are to win. 16 ways to win and 20 ways to lose is basically what we need to have written down. It's not a wise bet. It's not the worst bet in the world either, you know. I mean, it's close, you know. It's not like there's only 2 ways to win and 34 ways to lose, you know. But if you bet on it as forever and ever and ever, like if you bet on it every time, you would lose way more times than you would win in that situation. So that's the house advantage. Look at the trickeration though, because there's only like 5, 6, 7, and 8 are the only numbers not on there, but look how many possible ways there are for 5, 6, 7, and 8. So coin flipping. Suppose a person is to flip a fair coin and let it land with no interference. What is the probability it lands on heads? Well, there is only one head out of the 2 possibles, heads or tails, so that's 50%. Pretty basic, right? Yolanda's going to flip the coin 2 times in a row. Draw out all the possibilities. So let's figure out how many possibilities there are. Again, it was like possibilities to flips and stuff like that, or you can do it like this in blanks. It's like, alright, she could flip the first coin, there's 2 possibilities for that, and flip the second coin, there's 2 possibilities of that, heads or tails, you multiply this together. Isn't there 4 total things that could happen in this situation? So, let's do heads, and then they could flip a heads and a tails. That's if they flipped a head every time on the first one. Well, now if they flipped tails on the first one, you could do tails and heads, and tails and tails. Right, there's our 4 possibilities. Find the probability of flipping tails and then tails again. So boom, boom. Now we need their probabilities. It's a 50% chance to flip tails, and then it's a 50% chance to flip tails. So 0.5 times 0.5 is going to give us 0.25 in that situation. So 0.25 is a 25% chance. Find the probability of flipping at least one head. Well, again, let's take that little shortcut. The probability of flipping at least one head is 100% minus the flipping no heads, right, which is both tails. So 100% minus 25% would give us 75%. So there's a 75% chance. Because again, if you flip at least one head, it's bing, bing, bing. All of those have at least one head. This is the only one that does not have at least one head, so no heads in that situation. All tails. John has 2 10-sided dice numbered 1 through 10 on them, and they're fair. How many possibilities are there when you roll it? So what you can do is you can do the blanks again, you know. On the first die, it's 1 through 10, so isn't there 10 different numbers there? And on the second die, there's 10 different numbers on it. So you multiply those together, and isn't there 100 different combos? It's just like the chart we made on the first problem. It was a 6-sided die and a 6-sided die, where there was 36 total. Well, now a 10-sided die and a 10-sided die. So 100 total. All right, more in deep with combinations and permutations. We've got these fancy schmancy formulas here. And the big thing to remember is who's who. A combination, order doesn't matter. We'll kind of talk about that as we go through the problems. And in a permutation, order is important. So how do I remember those? It's like perm important, like when you go perm your hair, that's apparently important to people. I don't know why I remember it that way, but I do. So combinations is where we need the fancy formula, and permutations we could use the counting method. Like there is a fancy formula for it, but I would rather use the counting method. That's our blank system that we've been dealing with. So let's kind of talk about this. Let's see how we can figure out if order matters or if order doesn't matter. A group has 4 people in it: Abby, Bill, Cheryl, and Daryl. List all the ways to have a president and a vice president, and we'll see if order matters. So let's just pick on like the president first. Let's just kind of go in a nice sequential order that Abby's going to be the president. So we can obviously abbreviate the names A, B, C, and D since they start with that. Let's say Abby's the president. Now who could be her vice president? Well, Bill. Well, it could also be that Cheryl was the vice president, and it could also be that Daryl was the vice president, right? So there's 3 combos right there, just if Abby is the president. Well, what if Bill was the president? So if Bill was the president, now here's a question. Abby could be her vice president. Does order make a difference in that situation? It's like these are the same 2 people, Bill and Abby, Bill and Abby, but doesn't order make a tremendous difference? Because in this case, Abby's the president and Bill's the vice president, and here Bill's the president and Abby's the vice president. So doesn't order make a difference in that situation? So order matters. So Bill could be the president and Cheryl could be the vice president. Bill could be the president and Daryl could be. So there's more possibilities. Well, now, what if Cheryl was the president? Couldn't Abby be her vice? And Bill could have been the vice, and Daryl could have been the vice. And then also, Daryl could be the president, Abby could be the vice, Bill could be the vice, and Cheryl could be the vice. So as you can see, you kind of see the combos. You're like, well, you see a C and a D and a D and a C, but since order makes a difference, like all these different combinations uh, are different, so that's not why it's called a combination. I'm sorry, I used that word. That's called a permutation, right? Because order is important in that situation. How could we have figured that out? Well, there's 3, 6, 9, 12. How could we have figured that out? The counting method. Like how many people could have been the president? 4. How many people could have been the vice president? 3. And boom, multiply those together, and there's your 12 different scenarios. But now check this out. Okay, so these people are in the class. I guess they were a group. I kind of have a typo here, but say it's the same 4 people. Those same 4 people, 2 of them have been asked to go home and relax, right? How many different groups of 2 are there? Okay. Well, now it's like, check this out. Let's just use the drawn out example. If I say, yo, Abby and Bill, you can go home. Or if I say, no, Bill and Abby, you can go home. Isn't that the same group? It's like the order doesn't matter when you pick that out. So what we have is what's called a combination, and we have to use this formula. It's n factorial over n minus r factorial times r factorial. Man, that looks complicated. It is so not complicated. N is the number of items you want, and R is the way they can be ordered, right? So let's do it like this. We want, hold on. Yeah, sorry, I read that wrong. I didn't seem right when I said it. You have n items. N is the total. Yeah, n is the total, and R is the ways you want. You want to find R ways, so R is what you want. So, sorry. I knew that sounded funny when I said it. I was like, that didn't sound right. So I want to make sure I didn't have it typed wrong. But you have n items. N is the total. So, all right. You have how many total classmates? 4. So n equals 4. If this helps, we can say n equals 4. And we want 2 of them. So it's going to be 4 factorial because that's our n. And then we got to do n minus r. Isn't there really 2 in that situation? If you do n minus r factorial times r factorial, which is what you want, so 2 factorial. So once we do a few of these examples, this will be way more easier than you think in that situation. So 4 factorial, math, newt, 4, it's 24 over 2 factorial is 2 times 1, which is 2 times 2 factorial, which is 2 times 1. So 24 divided by 4, which is 6. Now this should definitely be less than what we had before. And the reason why is because we basically, well, we did the permutation formula right here, but then you had to divide it by another 2 because it's like, okay, A and B showed up twice, A and C show up twice, A and D show up twice. You know, it's like everybody showed up twice because you had like president versus vice president. Well, now that order doesn't matter. There's only 6 different groups. If I say Abby and Bill, you can go, okay, or I can say Abby and Cheryl, or I can say Abby and Daryl, or etc. You know, it's like there's only 6 different groups. So since order didn't matter, we're using the combination formula. All right, let's try again. A club has 5 people in it, A, B, C, D, and E again. How many ways could the president, vice president, and secretary be elected? So they don't ask us to list it all out. They just say how many ways. All we have to realize is it a permutation where order matters and we can use the counting method, or is it a combination where we got to use the formula? Doesn't order matter? Like you're selecting a president, vice president, and a secretary. So order matters, counting method, permutation. So president, 5 people could be that, 4 people could do this, and 3 people could be the secretary. So we punch that in. That's 20 times 3, which is 60. So 60 ways. There are 60 different ways that we could elect that. Now, club members have been asked to sing a song, list all the possible groups of 3. So, all right, if Alex, Billy, and Chuck were this way, it doesn't matter if it's Alex, Billy, and Chuck singing, or Chuck, Billy, and Alex, or Billy, Alex, and Chuck. The order doesn't matter what these 3 people are in because they don't have a specific job. Like everybody's just in this group singing a song. So this is a combination, you know, if you like want to maybe write that down, and we'll use this formula. The total, 5 people, so that's going to be factorial, over, we're choosing 3, right? So n is 5 and r is 3. So that's going to be 2 factorial, because it's n minus r factorial, times 3 factorial. And here's something you'll notice. These two numbers, like the 2 and the 3, should always add up to be the total. It really doesn't matter like what order they're going to be in. So we call this 5 choose 3, right? There's 5 people and we're choosing 3, so it's 5 choose 3. And what we could do is do a little cancellation project. Remember, if you're going to have 5 factorial over 3 factorial, I'm just going to kind of write that out again. 5 factorial is 5, 4, 3, 2, 1, all being multiplied together. And you got 2 factorial down here over 3 factorial. Well, isn't all of this and this like totally cancel each other out? Because that's 3 factorial, that's 3 factorial. So you really got 20 over 2, which is 10. Because I feel that we can do most of this by hand instead of rushing to the calculator because of the cancel policy and dealing with small numbers. Like 2 factorial is just 2 times 1. Like why would you punch that in your calculator, and etc. So let's try again. Feeling hungry, you call Popular Pizza Palace to order a pizza. They brag of their 12 different toppings. You're going to choose 4 toppings. How many different combinations do you have to choose from? So there's 12 total and you're choosing 4. The only question is, does order matter? Like if you want to get pepperoni and cheese and hamburger and mushrooms, does it matter what order they put them on your pizza? I don't think so, man. So it's 12 choose 4, which is a combination in that situation. You're not going to pick any topping more than once in this problem also, so we're using this formula. 12 total over, you're going to do 12 minus 4, which is 8 factorial, times 4 factorial. Because it's n minus r, here's 12 choose 4. Let's say you actually wrote it like this, 12 factorial over 4 factorial times 8 factorial. That's the same thing, you know. And honestly, that's how I write it when you check my answer key, because it's like I'm doing, oh, 12 choose 4, so I need a 12, I need a 4, and then there's 8 left over because you have to do some subtraction. So what ends up happening is all of the 8 factorial is like totally gone in that situation, and you have 12 times 11 times 10 times 9 upstairs. So we'll do that. 12 times 11 times 10 times 9, which is 1180, 11880 over 4 factorial, which is 4 times 3 times 2 times 1. If you need to punch that in, you can, but 4 factorial is going to be 24. And then you just kind of punch that in, 11880 divided by 24. And there's 495 different ways you could order a pizza then, if you're choosing 4. That didn't circle the answer. So if you're gonna choose 4 toppings out of the 12 and you don't repeat any topping, 495 different ways you could do it. Cool. Coach K has 12 members on the basketball team. How many different starting lineups of 5 people could be formed? So real quick, let's just call those people A, B, C, D, and E. He's going to pick 5 people. If these 5 people are playing on the basketball court, it really doesn't matter what order he selects them in. Now, I do understand that it's like, well, who's the center? Who's playing guard? Who's playing this? I understand that, but it's like the 5 people that are out on the court are still the 5 people out on the court. It doesn't matter what order they're in. So order doesn't matter, man. Order doesn't matter. It's 12, choose 5. So that's a combination. Order doesn't matter. 12 factorial, choose 5 factorial, and then you need the leftovers, 7 factorial. These two numbers, the 5 and the 7, have to add up to be 12. So if we try to punch that in our calculator, it's probably going to have an overflow error, So that's why I do the simplify. I'm going to get rid of the 7 factorial, and this is going to be 12 times 11 times 10 times 9 times 8. I got all the way down, and you don't need the 7. So I'm going to punch that in. So actually, I have that right here. 12 times 11 times 10 times 9. I just need to take 11880 times 8, and that'll give me that number, 95040 over 5 factorial. I'll punch that in. 5 math probability 4 120, and then I'll divide that out. 95040 divided by 120. 792 different ways. So if 12 people choose 5, he has a possibility of 792 different starting lineups he could choose. And lastly, there are 10 people in a group. How many ways can president, vice president, and secretary be selected? Order totally matters in that, so that's the blank method. The counting method is really what it's called. You could choose 10 people for the president, 9 people for the vice, and 8 for the secretary. And just to kind of show you how that formula works here, it would be your total 10 factorial over, like, if you're choosing 3, they just do, all right, I want n minus r, so n is 10, and r is 3, it's over 7 factorial. And that totally simplifies to be, since 7 factorial cancels out, you have 10 times 9 times 8, and then the rest is your 7. So that formula and the counting method are the same thing. It's just the counting method is much faster. So we punch that in. 10 times 9 times 8. Boom, 720 total ways. If the group ran a 5K race, how many ways could they finish amongst themselves? So everybody's running. 10 factorial, baby, right? That was just like last time. So 10 math factorial. Holy cow. 3628800. 3628800. Comma, over 3 million ways. That's awesome. If they're going to take a picture in a group of 3, how many pictures are possible? So let's say A, B, and C. Now, this is a good arguing point. It's like, if these 3 people are in a picture, does order really matter? It's like, I get it, because it's like, well, if A is on the left and B is in the middle and C is on the right, isn't that a different picture than A, C, B? It's like that's a different picture, but it is like the same people in the picture. Sorry, it's like the same people in the picture. So we're just going to say how many pictures of this group are possible. So it's the same three people in the group. But if you can argue with me and prove your point, like I'm not going to mark it wrong then. If you're like, no, I really feel this, because of this, this, and this, and if I feel that's a good argument, I'll say, all right, I'm cool with that. So I feel we're just doing groups, so order doesn't matter. It's 10 choose 3, right? So combinations. So 10 factorial choose 3 factorial, and won't there be 7 factorial that we have to divide out. So cancel in that, and this would be 10 times 8, times 9 times 8, which is 720 because we figured that out, divided by 3 factorial. 3 factorial is 3 times 2, which is 6 times 1, so 720 divided by 6, and I think that's 120, baby. Yeah, 120 different people. So all right, man. That's that in a nutshell. Let us know if you have any questions, and have a good one.